Hi there. So welcome to 6.4, which is on rational and irrational numbers. We are going to start by talking about the Pythagorean theorem. And this is going to be sort of woven through some of the sections at the end of this class, and then it's also going to be woven through Math 149 if you go on to take that class. So the Pythagorean theorem, I'm sure many of you have heard this before, but it's totally fine if you haven't. We're going to just go over it from the beginning. It's a theorem that is applicable to right triangles and right triangles only. So when I say right triangle, I mean any triangle where there's a right angle. And you should see on the diagram, you should see this box that indicates the right angle, so a 90-degree angle. The triangle needs to be labeled with that so that you know it's a right triangle. Otherwise, if you're not sure, like if you saw a picture that maybe, I don't know, looked like this, and maybe this angle right here, you thought it was 90 degrees, but you weren't sure. If it's not labeled, you can't assume that it's a right triangle. So make sure that it's a right triangle first. Once you have a confirmed right triangle, then we know that this is true right here, this theorem. So a squared plus b squared equals c squared. What does this mean? Well, the a and the b stand for what we call the legs, the lengths of the legs, and the legs are always the shorter of the two sides. So like on the triangle that I just drew, we've got a leg here and a leg here. So we could call this A and call this B. It doesn't matter which one's A and which one's B. The important part though is identifying where the hypotenuse is, which is the longest side, and we always call that C. So C in this picture, we say hypotenuse. And usually with most right triangles, you can see clearly that the hypotenuse just looks longer. It's not always the best way to go about things in geometry because sometimes, things can be deceiving and you might not be sure. If you're not sure, you can always look at where the right angle is, and whatever side is opposite from that right angle, that's the biggest angle, so it's going to open up to the longest side. So that's another way to identify where the hypotenuse is. So make sure that when you're doing the Pythagorean theorem that your hypotenuse, that length is always by itself on the side opposite from the side of the leg. So let's go ahead and do some examples. So example 1, we've got this triangle with legs 6 and 8. I know they're legs because those are not the hypotenuse. That's not the shortest side. And it says use the Pythagorean theorem to find the missing length. So I'm going to call this one C. And we were already started right down here with the Pythagorean theorem. So we did 6 squared plus 8 squared equals, and we're going to call that c squared. And then we're going to go ahead and solve that. So to solve that, we're going to square both of these. So I'm going to say 36 plus 64 equals c squared. I add these two together, which equals 100 equals c squared. And then at this point, just ask yourself, well, how do you get rid of that square? So how do you get just the c and not the c squared? We have to do the opposite or the inverse operation. So squaring and square rooting are inverse operations. So to undo squaring, we're going to square root that side, and to make the equation balanced, we're going to square root the left. So you square root both sides to undo a square. The square root of 10, or square root of 100 is 10, and square root of c squared is just c, so that means our hypotenuse is 10. But then just to double check, I'm just going to draw this bigger. You can always just take your calculator, do this by hand real quick, do 6 squared plus 8 squared equals 10 squared, and see if that ends up working out to be true. And in this case, it does. So it's always good to double check. Let's look at the next one. So the next one, it looks like we have the hypotenuse is our 13. That goes by itself on one side. And then our legs are going to be 12, and then our unknown. So we could call that unknown A, this side right here, A. So we've got A squared plus 12 squared is 144 equals 13 squared is 169. Now this one's a little bit different than the last one because our unknown has a number with it on that side. So we're going to subtract 144 from both sides so we can get the a squared all by itself. And then 169 minus 144 is 25. And then just like before, we're going to do the square root, take the square root of both sides to undo that squared. So square root of a squared is a, square root of 25 is 5. And then to double check, we've got our triangle So 12, 5, and 13. So we're going to do 5 squared plus 12 squared equals 13 squared. We're questioning that. So 25 plus 144 equals 169, and then these two together are 169. So that ends up working, so we got the right answer. So then the last one, let's identify where the hypotenuse is. So ask yourself, what side is the longest side? It's the opposite from the right angle. So the longest side is going to be 34. That's our C. So notice that's by itself down in the equation. And then we've got 16 squared plus, we'll call this B. B squared equals 34 squared. So 16 squared is 256 plus B squared equals 34 squared is 1,156. And then we want to get the B squared by itself, so I'm going to take off 256 from both sides. And then those cancel, and you're left with B squared equals 900. And then you're going to take the square root of both sides, and you're going to get B equals square root of 900 is 30. And then we can always double check our work like we did last time. So 16 squared plus 30 squared equals 34 squared, which it does. Keep in mind, so I ended up getting some nice answers for these. They make good example problems when we're starting, but keep in mind that the legs of a triangle don't always have to be whole numbers. So if you're doing some practice problems and you get an answer that's not a whole number, it's totally fine. It doesn't mean that you did something wrong. It happens all the time. So down here, and I'm just going to erase this so we can see it a little bit better. You'll notice it says the converse of the Pythagorean theorem. So the converse is kind of like the opposite. It's when we reverse the theorem. So the Pythagorean theorem, let's just go back real quick. So Pythagorean theorem said that for any right triangle, so if you have a right triangle, then this is true. The converse is if the sum of the squares, I'm just going to write this in math terms. So if a squared plus b squared equals c squared, then the triangle is a right triangle. So basically all this says is if you have a triangle, so I'll give you an example. Let's say you have a triangle and it's 3, 4, 5. Okay, but you don't know if it's a right triangle, so you're questioning that. What you can do is you can do the Pythagorean theorem using the sides you think are legs in the hypotenuse that you're suspecting. So 4 squared plus 3 squared equals 5 squared. And actually it's not really suspecting because 5 is bigger, so if it were a right triangle, that 5 would have to be the hypotenuse. And then we go ahead and we work it out. So 16 plus 9 equals 25. 16 plus 9 is 25. So when I do this, it ends up working out. So you say, yes, it's a right triangle. So that's confirmed. It also can work the other way where maybe it doesn't work out. So maybe you have a triangle, and I'm just making this up. Maybe this is 1, 2, and I don't know, 4. So I would have 1 squared plus 2 squared equals 4 squared. So I get 1 plus 4 equals 16. 5 does not equal 16, so this is not a right triangle. So you can use it to prove that a triangle is not a right triangle too. So square roots are thrown in this section too, just because, I mean, you've noticed we've already done some square roots just in solving using the Pythagorean theorem. So it makes sense that, you know, these two are combined together. So let's talk about what a square root is, and then we'll do some practice problems. We're going to simplify them and learn how to rationalize denominators that have square roots. So a square root of a number of a, okay, and we'll talk about what the principal square root is in a minute. A square root of a is defined as square root of a equals b, where b squared equals a. So what does that mean? Basically, I'm just going to give you an example. So the square root of 16 says what two numbers, what number when multiplied by itself gives you 16? Well, 4 does. So the square root of 16 is equal to 4. There's also another number that when multiplied by itself it gives you 16. So think about that for a minute. What's one other option besides 4 that when you multiply that number by itself you end up getting a positive 16? The answer is negative 4. A negative times a negative is a positive. 4 times 4 is positive 16. So technically, the square root of 16 is positive and minus 4. Both of those end up working. Now, usually, well, maybe not usually, but I would say most commonly, you just see the positive, and that's called the principal square root. So this one right here, so the square root of 16 equals 4. This is called the principal square root. But negative square root, or negative 4, is also the square root of 16. So example 2 says find the principal square root. So that just means the positive answer. We don't have to list the negative. And the negative square root of each number. So the square root of 49 is equal to, and ask yourself what times what gives you 49. So 7 times 7 and negative 7 times negative 7 both give you 49. So the answer is plus or minus 7. So positive 7 and negative 7. How about square root of 1/4? So what times what gives you 1/4? And I'll write it down here again. So 1 times 1 gives you 1. 2 times 2 give you 4. If 1/2 times 1/2 gives you 1/4, then negative 1/2 times negative 1/2 also gives you a positive 1/4, since a negative times a negative is a positive. So 1/2 is the principal square root. So our answer here is 1/2 and negative 1/2. And then this one, we weren't asked to label it, but that one's the principal square root since it's the positive answer. So what happens, we've multiplied two whole numbers, but we haven't multiplied two square roots yet. So let's think about what that would look like and what type of answer we would have if we multiplied two square roots. So for example, let's say I had square root of 4 times square root of 4. What would happen? So square root of 4 is 2, square root of 4 is 2, 2 times 2 is 4. So square root of 4 times square root of 4 is 4. Let's try that again with a different square root. So let's do square root of 16 times square root of 16. So square root of 16 is 4. Square root of 16, oh, you know what? I said 16 and I wrote 14. That's confusing. There we go. Okay, so that's positive 4. 4 times 4 is 16. So is that a coincidence that whatever number was underneath the square root is the answer? It's not a coincidence, because the other way to write this is the square root of 16 squared. And like I said at the very beginning when we were doing Pythagorean theorem, square rooting and squaring are inverse operations, so they cancel each other out. So that square cancels out that square root. So in general, the square root of b times the square root of b is just b. So if we look at example 3, the square root of 14 times the square root of 14, you just get 14. And if you don't believe me, you can take a calculator. So if you ever forget this property, you can certainly put in the square root of 14 in the calculator, which gives you a really crazy answer. It's not a whole number, but if you multiply that by itself, you're going to end up getting the 14. Same thing here. So the square root of 3/2 squared is just 3/2. That square and the square root just cancel each other out. This one was going to be 2.3. And then the square root of 0 squared is just 0. So don't be afraid of the square root of 0. The square root of 0 is just 0. But this square root and square, those end up canceling each other out. So I just mentioned the square root of 14 is a crazy number. I was going to use another word, but I didn't since we haven't talked about it yet. But the other word that I was thinking of was irrational. So when you think of the word irrational, think of what comes to mind when you just hear that word in general. So not associated with math. Like if I say to a person, you're being really irrational right now, what does that mean? It could mean that they're just not making any sense. Okay. The same is true with numbers. So a number that is irrational is a number that goes on forever and doesn't repeat. So one of the most common irrational numbers which I actually have down here, is pi. So 3.14159, and it keeps on going. So it's a number that doesn't repeat and it doesn't end, and that's called irrational. So, and I have that here in a box. A rational number is a real number that cannot be written as a ratio, so it can't be written as a fraction, and they're non-repeating and they're non-terminating. Terminating means end. So that non-repeating and non-terminating means they don't repeat and they go on forever. And they can't be written as a fraction. But this right here, this is the important part. You don't even want to try to write it as a fraction. You can just identify whether or not it repeats or it ends. And then this up here in this box, it says if p is a prime number, then the square root of that number is irrational. The square root of any number that's not a perfect square is going to be irrational, in addition to prime numbers. So, for example, the square root of 15 is going to be irrational. 15 is not prime. It's divisible by 1, 3, 5 in itself, but it's irrational because and you can put that in the calculator just to double check. So let's just do that real quick so we can see what that would look like. So if I do 15, and with this calculator I have to put the number in first and then this key. Every calculator is different. You can see this number, it keeps on going, and it stops eventually because the screen is only so big, but it will keep on going forever, and it looks like there's no pattern here to the numbers, so that means that's an irrational number. So I'm just going to add here, if p is a prime number, then the square root of p is a rational number, and I'm just going to add the square root of any number that's not a perfect square. So if you don't get a whole number answer for the square root, then it's going to be irrational. Well, I shouldn't actually say that. Not necessarily a whole number, but if you get an answer that ends or repeats. So let's go down to example 4. So let's do some of these. So let's look at each number. Let's look at this first one, and I want you to ask yourself, does it end? It doesn't end, so it keeps on going because you see the ellipsis, the 3 dots, so it keeps on going, so it's not terminating, but it's got to at least repeat if it's going to be rational. So 0, 0, 6, 0, 0, 6, 0, 0, 6. So I'm going to say that this is a rational number because it repeats. So a rational, I'll just put in parentheses because it repeats. Okay, this next one, 0, 0, 0, 6, 0, 0, 6, 0, 0, 0, 6. So there's a pattern here, but you don't have a repetition of the same digit. So for example, if it was 0, 6, 0, 6, 0, 6, 0, 6, you'd consider that a repetition. But this is changing. It goes from 0, 6 to 0, 0, 6 to 0, 0, 0. So this one you're going to say is irrational. So it doesn't repeat the same thing, the exact same digits. This one terminates, it ends, so this is rational. And remember with decimals, you can just look at the place values. So tenths, hundredths, thousandths, 10,000ths, 100,000ths. So that's the denominator, and then you can just put the numerator on the top. So 1001, or the number as the numerator, I mean. And there you go, you got your fraction, your rational number. Okay, this one, 0.73737373. So it goes on forever, but it repeats. So I'm going to say rational because it repeats. Okay, with this one, 0.21060606. Now this one is also repeating. So you can, and one way to think about repeating is if you can use a bar to write the number. So for example, 0.2106. The 06 is the part that repeats, so we could put a bar over there. So if you can write it like that, like this one right here, we can write like that. This one up here, 0.006, we can write with a bar. So we can say that these are all rational numbers. And then this one looks like I see some repetition, but it's not the exact same number combination each time. So 0.731, 7311, 73111. So I'm going to say this is irrational. So let's look at some other types of numbers besides decimals. So classify each number as rational, irrational, and if it's irrational, basically what they want us to estimate the answer. So the square root of 81 is 9. So 9 times 9 is 81. So this is going to be a rational number. 9 can be written as 9 over 1. And so anytime we get a whole number, that's going to be a rational number. Now square root of 10 does not have a root. There isn't a number that you can multiply one number by itself to get 10. So let's use a calculator and just approximate what the answer would be. And we can also verify that the number is non-repeating and non-terminating. So 10, and we press the square root button. You can see that this is an approximation, so we can approximate a number that when multiplied by itself it gives you 10, but this keeps on going forever and ever, and it doesn't look like there's the digits repeat. So to estimate, it says find the approximation to the nearest tenth. So I'm going to say square root of 10 is approximately 3.2 if we round that. So we're going to say approximately 3.2, and it's irrational. 10 is not a perfect square. Okay, square root of 4/9. This is a good one because this is why earlier when I had said, oh, if you don't get a whole number, that's a problem, and then I kind of backed up and thought, well, no, we don't want to only think of whole numbers as appropriate square roots because, or answers to square roots, because it is possible, like in this example, we can take the square root of 4, which is 2, and square root of 9, which is 3. So we get an answer here. We get a rational. This is a rational number. Square root of 4/9, that's not a whole number. So it doesn't have to be whole, but we do have to be able to find a square root for those numbers. So they have to be, and this ends up working because 4 and 9 are both perfect squares. So the key is looking for perfect squares. So similar here, 16 is a perfect square, so I'm guessing 0.16 is a perfect square. And you know, if you weren't sure, like this is where you could it'd be totally appropriate to use a calculator. So you could do 0.16 square root and you get 0.4. So 0.4 times 0.4 is 0.16, and this is rational because the decimal is terminating. It doesn't go on forever, and then yeah, as long as it's terminating, then we know it's rational. So we talked about square roots. Let's just jump in and talk about cube roots. So this is something you may or may not have done before, and it's totally okay if you haven't. This is something that, you know, you might, it would be brought up more so in middle school than elementary school, but you could definitely do this with some fifth graders. They would just be optional. It's not part of the fifth grade curriculum, but they could definitely touch on this, I think. So a cube root, the idea of a cube root is just, well, first it's written like this. So it's written with a small 3 and then the square root symbol and then a number underneath. We'll call it n. And the answer to this, we say this is a number s, such as s times s times s gives us the number underneath, okay? So let's do some examples that don't use variables because it'll make more sense. So if we do the cubed root of 8, we're looking for a number times itself that gives you 8. So what times what gives you 8? Well, the answer is 2 because 2 times 2 times 2 gives you 8. So cubed root of 8 is equal to 2. Now with cubed roots, we can think about the different signs. Now with square roots, for example, if you have the square root of 16, we said that could be 4 or it could be negative 4. Well, can the same thing apply here? So what about negative 2? Negative 2 times negative 2 times negative 2. Well, a negative times a negative times a negative ends up giving you a negative, and we don't want a negative 8. So 2 is actually the only answer for cube root of 8. So it's a little bit different than square roots in that sense. Let's do one more. So the cube root of 27. So what number times itself gives you 27? The answer is 3. So 3 times 3 times 3. So one thing that might be helpful, so depending on your calculator, I actually don't have a graphing calculator that I can pull up here, but the graphing, I'm just going to write down some notes here. If you have a graphing calculator, so like a TI 83 or 84, what you can do to find the cubed root button is you can go to its math. And I'm going to pull it up on my calculator right now so I make sure to tell you the right thing. So it's math, okay, and it's right in that menu. And if you go down to number 4, you'll see a cubed root like this sign. And so what you want to do is you want to press, if you want to do one of these in your calculator, you hit math number 4 and you select this sign, and then you'll type in whatever number that you want to take the cube root of, and then you'll be all set. If you have I know like with my scientific calculator on the computer, I don't have a cubed root button, but one way around that is you can use an exponent. So I'm going to jump ahead of this box down here, nth roots, and then I'm going to come back and do example 6. So the cool thing about a square root is you can actually write a square root as an exponent. So and that's what this explains down here. So the nth root of b is the same thing as b to the 1 over n. So let me do a couple examples. So the square root of 16 is the same thing as 16 to the 1/2 power, because the 2 in the denominator here in the fraction corresponds to the square root. If we want to take the cubed root of 27, that's the same thing as 27 to the 1/3 power. Okay, so if you had a calculator that looks like, it was just a scientific calculator like this one, what you could do is you could do, let's see, I think you have to do 27 and then this button right here, the exponent button, and then I'm going to use a parenthesis and I'm going to do 1 divided by 3, so the 1/3 power, and I'm going to hit enter, and you end up getting 3. So 27 to the 1/3 power is equal 3, which is what we found up here. You can just do that by hand, but I just wanted to show you how to do that with the calculator. So it's easier to look at on the graphing calculator, but definitely not impossible with just a basic scientific calculator. So let's look at example 6. So the cubed root of 30 is a number times itself to give us 30. So let's think if we can actually find if that has a cubed root. So we know that 2 times 2 times 2 gives us 8. We know that 3 times 3 times 3 gives us 27. Okay, we're trying to get 30. Well, if we go up to the next whole number, 4 times 4 times 4, 4 and 4 is 16, times 4 is 64. We're not getting 30 there. So notice 3 times 3 times 3 gives us 27. 4 cubed gives us 64. So my guess is the answer to this is going to be really close to 3, since 27 is close to 30. And then we could use our calculator because it says approximate it to the nearest tenth. So let's just do, I'm going to do the scientific calculator. So I'm going to do 30 and then this button to the 1/3 power, since it's the cubed root, and then enter. And we end up getting 3 if to the nearest tenth would be like 3.1. So I'm going to say approximately 3.1, and that's kind of where I thought it would be, since 3 cubed is 27, 3.1 is really, really close. Okay, let's try this one. So what times what times what gives us 125? Okay, I know 4 times 4 times 4 is 64. Let's try the next number, 5 times 5 times 5. If you multiply those together, you end up getting 125. So your answer here is just going to be 5. And then the last one, 100. So what number times itself gives us 100? Can we find a number so that's true? Well, we can continue our pattern over here on the left-hand side. So when actually we don't even need to. So 4 times 4 times 4, 4 cubed is 64, and 5 cubed is 125. Well, if we're trying to get 100, that means it's going to be somewhere between 4 and 5. So at this point, I'm going to use my calculator. So I'm going to do 100, the exponent key, 1/3 power, and I get a decimal. So 4.6 approximately. So that looks like an irrational number for the last one and the first one. Okay. So speaking of a rational number, this is a great time to talk about just numbers in general and kind of go back to all the names of the different groups of numbers that we talked about so far, and we can put them into this nice diagram. So real numbers, we haven't mentioned that before in the class. A real number is basically any of the number systems that we talk about in this class. So it's basically any number except a non-real number, which we're not even going to talk about in this class. And the students that you work with in elementary school are not going to see that term or that concept until they're in high school, until they're in Algebra 2, which is likely in 10th or 11th grade. So we have two main groups of numbers. So the real numbers can be split into rational numbers, which we call Q, and then and irrational numbers. So notice, so we've got rational numbers and irrational numbers. And then what we're going to do is we're going to draw these, remember in our set section, so in 2.1, we talked about how if a circle is inside of another circle, then we say that those are subsets of one another. So basically what this diagram represents is W, I'm just going to write down, so W is the set of whole numbers. And whole numbers are 0, 1, 2, 3, all the way up from there. Z is the set of integers. So that would be like -3, -2, -1. Okay. And then Q would be rational numbers. So what this says is that all whole numbers are integers, which if you look at the set, that's true. So all of these whole numbers, that's a part of this set of integers. And then all integers are part of the set of rational numbers. So Z is inside of Q and so is W. And that's what this sentence down here relates. So whole numbers are part of integers, are part of rational numbers, are all considered a real number. So example 7 says use these letters to indicate which sets each number belongs to. So -12. So I'm going to start on the very smallest set. So I'm going to start with the whole numbers and I'm going to work out. So is -12 a whole number? It's not, because it's not positive. So negative numbers are not whole numbers. Is -12 an integer? Yes, it is, because integers are negative and positive whole numbers. So I'm going to say it's an integer. And then from there, I actually don't even have to think about the other ones because I can just use the picture. So all integers are rational numbers and all rational numbers are real. So we can also say Q and R as well. Okay, the square root of 15. So 15 is not a perfect square. So if I put that in a calculator, I'm going to get a decimal. I'm going to get a decimal that doesn't repeat and doesn't end. So since that's the case, this is going to be an irrational number. So, and that's going to be, oh, you know what? I don't think I put a letter for that. So I'm just going to write irrational. There, I gotta go fix that. So that's going to be irrational, and that's also going to be real. So all irrational numbers are considered real numbers. And then 0.23, okay, so that's not a whole number. It's not an integer since it's a decimal, but it is considered a rational number since it's a decimal that ends. So I'm going to say Q, and then all Q are R. So it's a rational and real number. 130 is a whole number. So because it's a whole number, it's also an integer, it's also rational, and it's also real. 3/5 is not a whole number or an integer, but it is a rational number, and because of that, it's also considered real. 0.27, repeating, since it repeats, it's going to be a rational number, which is Q. It's not a whole number or integer since it's a decimal, but it is rational since it repeats, and therefore it would also be considered real. Square root of 10 is not a perfect square, so, and if you put this in your calculator, you get a decimal that doesn't repeat, it doesn't end, so it's considered irrational, and it would also be real. And then square root of 25, a 25 is a perfect square that's just equal to 5, so that's considered a whole number, and that means it also be an integer, rational, and real. So an integer, rational, and real for that one. Okay, so let's talk about some properties. So we've talked about these before with other types of numbers, but we're going to talk now about the entire real number system. So thinking about any type of number you can think of, like decimals, fractions, basically any number, in irrational numbers too. So the closure property. Remember that the closure property just says when you do an operation, you get an answer that's also in that same number system. So for instance, if you add two numbers, you end up getting, so if you take a real number plus a real number, you always get a real number answer. If you multiply, you always get a real number answer. Now for a minute, think about subtraction and division. So let's ask ourselves, does a real number minus a real number always give us a real number? Think, okay, is it possible to get a number that's not real, which would be like an imaginary number? And imaginary numbers have the letter I in them, so we write them like 2i, for example. And I, just so you know, stands for the square root of -1. So there's no way that we could get a number like that just by subtracting. So the subtraction is also closed under the real numbers. So let's think about division. So the only thing that's kind of weird about division, so with division, nearly all answers that you could get would be real. The only thing that gets a little bit weird is dividing by 0. So when you divide by 0 and you take any real number and you divide by 0, we say the answer is undefined. And so because we cannot divide all real numbers and get a real number answer, then division is not closed. So division we say is not closed because not all numbers, when we divide them, real numbers, you get real number answers. So let's think about the commutative property, commutative property. So commutative property, I've mentioned this before, but I always think about my commute to work when I'm trying to remember what this means. So I go to work, and then I, get my car and I come back the same route. And I use that visualization to show that if you just switch the order in which you do things, you get the same answer. So for example, let's think about what operations you would be allowed to switch the order of things. So if you had, let's see, I'm just going to make up some examples. 5.1 plus 2.3. Is that the same thing as 2.3 plus 5.1? It is. So we say addition is commutative. Okay. If we were to multiply 5.1 times 2.3, is that the same thing as 2.3 times 5.1? It is. Multiplication is commutative. Now what about subtraction? So I'm going to come over here. Is 3 minus 2 the same thing as 2 minus 3? It is not. So subtraction is not commutative. How about division? Is 3 over 2 divided by 2 the same thing as 2 divided by 3? It is not. So division and subtraction are not commutative, but addition and multiplication are. And the same thing is true with the associative property. So associative property has to do with the placement of parentheses. Addition and multiplication are associative. Division and subtraction are not. So for example, 2 plus 3.1 in parentheses plus, 5/3 is the same thing as 2 plus parentheses 3.1 plus 5/3. So I'm keeping the same order of my numbers, but I'm just switching the order of the parentheses. And the same is true for multiplication. So if I did a multiplication problem, 2 times 3.1 times 5/3, that's the same thing as 3.1 times 2 times 5/3. I can just switch. Oh, you know what? I just did commutative. You know what? Let me back up here. So 2 times 3.1 times 5/3, I'm going to write it like this, 3.1, so I can show my parentheses a little bit better. So associative means that you can place the parentheses in different locations. So notice I'm multiplying the same numbers in the same order, but the parentheses are in a different location. So because of that, and we get the same answer. So because of that, multiplication is associative. And then let's go down to, so these properties are very much the same as what we've talked about before. So identity, 0 is the additive identity. So for example, 5 plus 0 is 5. So with multiplication, 1 is the multiplicative identity. So for example, 5 times 1 is 5, and I'm going to just use a different color actually because I can. So here the important part is what's in red there. We call those the identities for addition, identity for real number multiplication. And then inverse, addition has an inverse. So 5 plus, we'll call it what, I'll do different color, is equal to the additive identity, so 0. So 5 plus what equals 0? Well, 5 plus negative 5 equals 0. So we say 5 and negative 5 are additive inverses. There we go. And then multiplication is similar, so we can say 5 times what is equal to not 0, but in this case the multiplicative identity, which is 1. So how do we get 1 there? 5 times what equals 1? If you want to cancel out the 5 and end up getting 1, we're going to have to multiply by what's called the reciprocal. And when we do that, we end up getting 1. And we can see that by just if we put this one over 1, then the 5s would end up canceling on the diagonal and we get 1. And so we'd say 5 and 1/5 are, I'll abbreviate here, multiplicative inverses. Okay, and then the distributive property, this is the same as what we've talked about before. It's just we're acknowledging that it applies to all real numbers. So it just means that if you have a number on the outside of the parentheses with addition or subtraction in the middle, you can take that outside number and multiply it by what's inside. So for example, 5 times 3 minus 2.5 is the same thing as, and I'm doing a subtraction example here, 5 times 3 minus 5 times 2.5. Okay. So, you know, with the properties, it's one of those things, I know we're going over them quickly, but they really do apply in elementary school. I mean, we start talking about properties even with kindergartners. So as much as like, you know, if I add, you know, the red block and then the blue block, you know, do I have the same number of blocks as if I start with the blue and add the red and that kind of thing. So when we really talk about these concepts all throughout elementary school. We don't always use their proper names, but sometimes we do, especially when kids get older. So let's go ahead, and we just got a couple more here. We're going to do some operations with square roots. And keep in mind, if you were taking an algebra class, I mean, you could spend a whole month talking about square roots. We're really just touching on this as a quick sort of review and a refresh. So example 8, classify each sum or product as rational or irrational, and if it is rational, evaluate the expression. So what we can do is we can use this property here, and actually, you know what, let's even, I'm going to skip that. We'll do the property after we're done with this example. So the first thing we can do is just try to evaluate. So the square root of 24 is 24 perfect square, and by perfect square, I mean numbers like 1, since 1 squared is 1, 4, 2 squared equals 4, 9, 3 squared equals 9, 16, 25, 36, 49, any number that you can obtain by squaring another number. So 24 is not a perfect square. And so we can't evaluate this anymore. So I'm going to say this is irrational. Okay. Square root of 36 is 6. So this is like 5 times 6. So we can say this is 30. And so that would be a rational number since it's a whole number. this one right here, square root of 14. 14 is not a perfect square, so this number is going to be irrational. Square root of 81 is 9, so 9 plus 18 is 27, so that's a rational number. Okay. Now what I want to do is I want to talk about this property in the box. So this property applies to situations where you have square roots that are being multiplied. And up here we didn't actually multiply two square roots together, so we didn't need it. But down here in example 9 we do. So for example, square root of 8 times the square root of 6 is just the same thing as the square root of 48. We can multiply those together. 12 times 3 is 36, so this is the square root of 36. Now sometimes this is helpful because 12 isn't a perfect square, 3 is not a perfect square, so I don't know these individual square roots, but 12 times 3 is 36, and I do know that square root, so I can get 6. So using this property allowed me to simplify this in a way that I wouldn't have been able to had I not use this property. So 6 is a rational number, and I forgot to write for the first one. Square root of 48, I'm going to say is irrational, since 48 is not one of these perfect squares. Square root of 5 is not a perfect square, neither is 20. So I'm going to multiply those together and get square root of 100. Now that is a perfect square. Square root of 100 is 10, so I'm going to say this is a rational number. I don't know, 6 and 10 are not perfect squares, so I don't know those square roots, but I can multiply and get square root of 60. Now square root of 60 is not a perfect square either, so that is irrational. And again, if you're not sure, if you're not really familiar with perfect squares, one thing I would do is just make this list. And you can make this list by taking and squaring all of the numbers. So 1, 2, 3, 4, 5 squared, 6 squared, 7 squared, 8 squared. Just list out what all of these answers are, maybe up to 10, just to become familiar. So the list here for perfect squares is all of these numbers here on the left. And then keep in mind you can also put these numbers in the calculator. So the square root of 60, if you weren't sure if that's irrational or not, put that in the calculator. And if you get an answer or number that doesn't repeat and doesn't end, you know it's irrational. Okay, so example 10, simplifying. So write each square root in a simplified form. So we really got to pay attention to the directions, because notice like in example 8, for example, we were classifying as rational or irrational. We didn't simplify these. In example 10, we're asked to simplify. So what does that mean? Simplifying a square root means to identify if there are any numbers that you can break this number down into so that you can maybe find the square root of those and simplify. So how do we do this? One method is to do a factor tree. So do a factor tree for 50. So 50 is 5 and 10. And remember, you can start by taking any two numbers and multiplying them together. And then when I get a prime number, I'm going to circle that number, and that means I'm done with that branch. So 10 is 5 and 2. So the square root of 50 is the same thing as 5 times 5 times 2. So anytime you have a repeat, or a pair of two numbers, like 5 times 5, you can pull one of them outside. So 5 times 5 is just like the square root of 25. Well, what is that? It's 5. So when we have a pair, we take one number on the outside. Square root of 25 is just 5. And then you can leave whatever is left over. So we have a 2 left, that goes on the inside. And so the answer is 5 times the square root of 2. And you can use a calculator to check your work on this one, just to make sure you didn't make any big mistakes. So the way you could do that is you could do the square root of 50. So 50 square root button is 7.07 approximately. So keep that number in your head. So 7.07. So we'll remember that number. And then we're going to do 5 times, and then we're going to do 2 square root of 2 equals, and we get the same answer. So that tells us that we simplified correctly. Now, it doesn't always tell us if we simplified all the way, but at least we know we didn't make any mistakes. So the square root of 54, I'm going to do factor tree. So 9 times 6 is 54. It can be broken down into 3 times 3, and then 3 times 2. And so square root of 54 is the same thing as 3 times 3 times 3 times 2. And so if I have a pair of something, I can pull one of those numbers out. So remember, 3 times 3 is just like the square root of 9, so that equals 3. So that's why I'm only bringing one of them out. And then if I don't have any pairs left, you can multiply whatever's left over. So 3 times 2 is left over, so that's 3 times the square root of 6. So in your calculator, do square root of 54, and you should get the same answer as if you do 3 times the square root of 6. And then last, let's do a factor tree for 80. So we get 8 and 10, 2 and 4, 2 and 2, 2 and 5. And so the square root of 80 is the same thing as we've got 1, 2, 3, 4 2's, and then we've got a 5. And so in this case, this is a good one to talk about. I've got one pair of 2's, so I bring out a 2. I've got another pair of 2's, so I bring out another 2. And then I don't have any more pairs, so I'm left with a 5 underneath. Well, what do you do with the numbers you pull out? If you have more than one, you're going to multiply those together. So you're left with a 4 times the square root of 5, and that's going to be the final answer. And then you can always double check square root of 80 in your calculator, and then 4 times the square root of 5 in your calculator, and you'll get the same answer. So example 11, we've got one more, is called rationalizing. So this is a trick that we can use to eliminate the square root in the denominator of a fraction. So it's not proper in math to leave a square root in the denominator of a fraction. It's kind of like, you know, if you have a fraction like 8 over 16, what do? Well, we simplify. We simplify by reducing this as much as possible, and that's just common practice. Well, another common practice in math is to not leave the denominator, not leave a square root in the denominator. So one thing we can do to eliminate it is to use that property that when you have a square root times itself, then you end up, the square roots go away. So all you need to do is you need to look at the denominator and ask yourself, well, what do you want to get rid of? You want to get rid of that square root. So in order to do that, I'm going to multiply this by itself so that the square roots go away. Square root of 2 times square root of 2 is just 2. And actually, you know what, I'm going to use a different color. There we go. And then if you multiply the bottom by the square root, then you've got to multiply the top by square root. And if you think about that, square root of 2 times the square root, or square root of 2 over the square root of 2, that's just 1. So I'm essentially just multiplying this initial fraction by 1. So I'm not changing it, I'm just changing the way it looks. So okay, so in the denominator I get 2, and then in the numerator 1 times the square root of 2 is just the square root of 2. So 1 over the square root of 2 is the same thing as square root of 2 divided by 2. So my answer is this. And again, we're just eliminating that square root in the denominator. And you could certainly use a calculator and do 1 divided by the square root of 2, and then square root of 2 divided by 2, and see that those equal the same answer. So this would be a great place to pause the video and try the next two on your own. So for the next one, I'm going to say times square root of 5 over square root of 5, okay, equals, so square root of 5 times square root of 5 is just 5, and then on the top I'm left with negative 6 times the square root of 5. Now, keep in mind that if the numbers outside the square roots, like these two numbers, if they can be reduced in any way, if they have a common factor, then you do need to reduce them. Negative 6 and 5 don't reduce, so the final answer is just this. Okay, so the next one, I'm going to multiply the top and bottom. I have root 7. And in the denominator, I end up getting 7, and then the top, I get 7 times the square root of 7. Now, I cannot reduce a number with what's underneath the square root, but I can reduce numbers on the outside. So I can divide both of these by 7, or just cross them off since they're the same number, and I end up getting 1 times the square root of 7 over 1, or just the square root of 7, since these end up just canceling out. So let me just show you real quick one common mistake that students will make. Like if they have something like this, they'll end up reducing these two numbers, and you cannot do that. Now if you had something like, let's see, if you had something like this, you could reduce the 4 and the 2, but you cannot reduce the 2 and the 6 because the 6 is underneath the square root. So almost think of that square root sign as just protective of that number, so you can't get to that number, but the ones on the outside you could. So this, you would divide both of these numbers by 2, and you get 2 square root of 6 over 1. or just 2 square root of 6. So I hope that helps. It made some sense. As always, let me know if you have any questions as you're doing your homework.